Good afternoon to all. I am Romila, Assistant Professor of the Department of Information Technology at Sri Muthukumaran Institute of Technology. I handle this subject this semester, Theory of Computation. The subject code is CS 3452. The regulation is 2021. So the core outcome of Theory of Computation is construct automata theory using finite automata and CO2 to construct models of regular expression and languages, CO3 to design context-free grammar and full-stone automata, CO4 to understand during missions and then capability, CO5 to understand undesirability and NP class problems. The syllabus of theory of computation is Unit 1 Automata and Regular Expression, Unit 2 Regular Expression and Languages, Unit 3 Context Free Grammar and Full Stone Automata, Unit 4 Normal Forms and Turing Machines, Unit 5 Undesirability. The continuing part of third unit is types of grammar and Chomsky hierarchy languages. The Chomsky hierarchy represents the class of languages that are accepted by different machines. So, in the various types of grammar is type 3 means the language is regular, the grammar also regular grammar. So, the machine is FSM and then NFA or DFA. So, an example of A star and B star. So the type 2 is context-free grammar in language. So grammar is here also context-free grammar. So in the machine is PD, push-down automata. And then one example for A power n and multiple by B power n. So type 1 is decidable languages. So grammar is context sensitive grammar and then machine is a linear bounded automata. So in the one example for A power n, B power n, C power n. The type 0 is computable languages. So the grammar is unrestricted grammar. So the machine is Turing machine. So the one example for n factorial. So the Chomsky hierarchy languages is the drawing is given C. First one is regular languages. Second one is context-free grammar. Third one is context-sensitive languages, and then computable languages. And then type 0 is unrestricted languages. So there is no restriction on the grammar rules. So they this type of languages. So the languages is effectively modeled by the Turing machines. So type 1 is means context sensitive languages. It is a three rules followed by and then first rule is the context sensitive grammar may be more than one symbol. On the left hand side the production rules, and then second rule is on the left hand side must not exceed the number of symbols on the right hand side. The third rule is A belongs to epsilon is not allowed unless A of is start symbol, so it does not occur on the right hand side of any rule. So the type 2 is a context free languages. So the context-free languages are the languages which can be represented by the context-free grammar, the CFG. So A belongs to alpha. So A is any single non-terminal, and A is any combination of terminals and non-terminal values. So type 3 is a regular languages. The regular languages means can be described using a regular expression. So in the regular languages is can be modeled by the NFA or DFA. So next one is derivation. So derivation means generating a string from the start symbol of a grammar, applying production rules the step by step. So how a string is formed using grammar rules. So the type of derivation is first one is leftmost derivation LMD. It is always replaced by the leftmost non-terminal values first. So second one is rightmost derivation RMD. It is always replaced the rightmost non-terminal values are first. So example for leftmost derivation, consider one grammar. A substituted by A of S substituted by A of B, and then A substituted by small letter A and capital letter A, and then small letter A. So B belong substituted by small letter of B. So generate the string AAB. So step by step leftmost derivation means first one is leftmost values is substituted first. So S is a start symbol. So S is substituted by AB. So and then A is substituted by A, small letter A, and then AB always here. So and then next step is, and the A means substituted by A. So WA I'm getting. So remaining B is this here. So and then third fourth step is AAB also here, and B is substituted by small letter B. So the string is finally the string is getting. So at every step the leftmost non-terminal is replaced by first. It's an important word. And then example for on the rightmost derivation, the same grammar is followed by S belong substitute by capital A, capital B. A belongs to capital small letter A, capital A, and then also small letter A, and B substituted by small letter of B. So generate the same string A, A, B. The step-by-step rightmost derivation means first one is right side values is replaced by the value the grammar. So the start symbol is S and then substituted by AB. So on the right side, so P is bust is substituted by the value of small letter B. So A B means, and then second right side is A, and then A substituted by the substituted by the A, substituted by the A. So and then fourth step is and the A, and then right side of one A. So A substituted by the small letter of A. The final string of AAB is getting. So in the every step most important rightmost non-terminal is replaced by first. So comparison between LMD and RMD. So replace first one is replace rightmost non-terminal, and then replace rightmost non-terminal. Second one is used in top-down parsing, and then used in top-up parsing. So expansion starts from the left. So and then rightmost derivation means expansion starts from right. So also it is called leftmost derivation, also it is called rightmost derivation. So derivation second next concept is derivation tree. It's also called by parse tree. So the tree representation is how a string is generated from the context by grammar. So see, root node is start symbol, and then internal node is in non-terminals, and then leaf node is terminal values is their final string also. So the example for one example for A, consider the grammar capital S substituted by small letter of A, capital letter of S, and small letter of B, and also substituted by the epsilon. So let us drive the string AAP. So the derivation tree means S is a start symbol. So S substituted by A, yeah, capital S and small b. So then S substituted by and then A, and then next time A S B, and then final step is S substituted by the epsilon. So the given grammar string is accepted by the derivation tree. So A B B. So the final string is getting. So the example for leftmost derivation tree. So the grammar is the production rule is yes substituted by capital A, capital B, and then A substituted by small a, capital A, and then also A, and then B substituted by small b, capital B, and then also B. So generate the string is triple A, triple B, in the leftmost derivation. So it is one memorable point. Always remember the leftmost non-terminal values is first. So step by step process for LMD tree. So S is a start symbol. So A B S substituted by capital A, capital B, and then leftmost derivation is first, so a substituted by small letter of a, and then small letter of a and capital A, and then b. So and the next step is leftmost derivation is, so a always here, and then a means yeah, small letter of A, capital letter of B, and then B. And then fourth step is A is here also, then A is here also, and then A means is substituted by small letter A once, and then last remaining is capital letter B. So final, and then for fourth process is A, triple A is here, and then and then B, capital B substituted by the small b and capital B. So and then next step is triple A is here, and then one B, and then B means once again small letter of B and then capital letter of B, and then last final step is triple A B. B is always here. So B means capital B means small letter of B. So the final string of triple A triple B is getting. So in the tree means start symbol, and then A B, and the leftmost termination, so A, and then B. A means A B. A means the small letter of A, small letter of capital letter of B, and then B means, and then B, and then leftmost derivation first, leftmost values is first, and then the reading leaves left to right. So on the given string is get it. So triple A, triple B is get it. So and then leftmost derivation tree. So the always replaced by rightmost non-terminal values is first. So the rightmost derivation tree. So the step-by-step process is we already know. So the final memory only one get in, rightmost non-terminal replaced every time is the first. And then the tree is a rightmost derivation tree is already know, and then rightmost values is a first value. So the final string is get in. So in the and the next topic is ambiguous grammar. So the ambiguous grammar means one strings can have a more than one parse tree. Note the point. One string can have more than one parse tree. So one or more than on leftmost and rightmost derivations is also getting. So example of ambiguous grammar is the consider the grammar capital E substituted by capital E plus E, and then capital E substituted by capital E star E, and then E capital E substituted by ID. So generate the string means ID plus ID whole power star plus ID. So the positive one is, and the higher first one is say higher priority. So the star production. So the E is the start symbol, and then E plus E. So E means already know ID, and then plus apparatus is also here, and then second E means E star of E. So and then E is means substituted by ID, and then star is here. So the E means substituted by ID. So ID plus ID star ID is a getting the string. So and then positive of second one is plus operation done is first. So ID plus ID bracket of and then star of ID. So first one is E is a start symbol, and then E star of E. So E means E plus E. So and then E will say ID, and then E means ID plus is always here, and then E means ID, and star is also here, and then ID. So the final string is ID plus ID star ID is a get. So same one more same part leftmost tree and rightmost tree is the same string is present this grammar. So this grammar is ambiguous grammar. So thank you so much.